Hey Phys 1 kids, Campbell here. In our second video on momentum, we're going to talk about the law of conservation of momentum and collisions. If you think about what we did in that class activity with the carts and the tracks, right, we were doing collisions. And if we have the carts, like this would be, this picture here of my little blocks, A and B, is kind of like our third scenario where we had cart 1 and cart 2 coming towards each other and colliding in the middle. And if you think about a collision, right, during a collision, there's a force. And by Newton's third law, the force that cart A applies to B has to be equal to but opposite of the force that B applies to A, right? That is Newton's third law, equal but opposite forces. And opposite means direction. If you think about collisions too, anytime there are interaction of forces, the time of interaction has to be the same, right? When those carts collided, the time of impact was the same for both. You can't have one impacting longer than the other. That just doesn't work. So that means if impulse is force times time, then the impulse of A on B has to be equal to the impulse of B on A. They're just in opposite directions because the forces are in opposite directions. If you remember back to our first video, impulse, besides being force times time, is also equal to a change in momentum, right? That's the impulse and momentum theorem, which means, therefore, that the change in momentum of B has to be equal to, but opposite, of the change in momentum of A. Remember that momentum is mass times velocity. So if we go ahead and we rearrange these so that I put all initials on one side and all finals on the other side, I get this equation that the initial momentum of A plus the initial momentum of B is equal to the final momentum of A plus the final momentum of B. This is called the law of conservation of momentum. The law of conservation of momentum says the momentum of an isolated system is constant. It's a great way to solve for speeds of objects before and after collisions. Now, what does this mean? The total momentum of an isolated system doesn't change. Well, we're going to talk more in class about momentum in 2 dimensions, but that means that when objects collide, like pool balls on a pool table, if objects go off at angles, then the momentum, because momentum's a vector, the momentum in the x direction has to be conserved, and the momentum in the y direction has to be conserved. But again, we're going to talk more about that actually in class, the x and y stuff. But what does it mean to be an isolated system? Because that's when momentum is conserved. Well, what an isolated system is a system in which there's no net external force. What's an external force? Well, an external force is a force that's outside the system that could change the momentum of the system. When we have a scenario like that, we want to use the impulse momentum theorem, that the impulse is equal to the change in momentum. So in that case, we would need to know information about that external force. I still don't get what an external force is, right? Well, let's take a look at an example. Let's take an example of Bob running and jumping onto a cart, kind of like jumping onto a skateboard. All right, if you think about it, if he sticks to the skateboard, him and the skateboard are going to move together after the collision of him jumping onto the skateboard. So here we have an example where Bob, who has a mass of 75 kilograms, is running at a speed of 4 meters per second. He jumps on a cart that's at rest, and then together they move off together. And I want to know, what is their speed afterwards? Well, in order to use the conservation momentum law, so the momentum initial equals the momentum final, we need to pick a system in which the momentum is conserved, in which there are no external forces. So what do I mean by that? So if we choose our system as just Bob, and we draw a free body diagram of Bob, we're drawing a free body diagram because we need to identify forces, right, and look for unbalanced forces. A free body diagram of just Bob would be his weight down, the weight of Bob, and the normal force up, which is coming from the fact that Bob's standing in the cart. So it's really the force of the cart on Bob, or the normal force. When Bob jumps on the cart, right, he applies a force to the cart that moves it forward, And the cart applies an equal but opposite force backwards so that Bob doesn't slip off the cart. And that force, this force right here in my free body diagram, right, is a friction force. If you think about it, if there wasn't friction, right, what would happen to Bob? He'd just slide right off that cart, right? In fact, then his momentum wouldn't change because there'd be no force. He'd just keep going. But there's friction, so Bob sticks to the cart, and him and the cart move together. Now, if we just chose Bob as a system, we have an external force. We have this unbalanced force on Bob that's changing the momentum of Bob. So we can't use the conservation of momentum, initial momentum of Bob equal final momentum of Bob, because that would mean that since Bob's mass doesn't change, right, he didn't get heavier himself jumping on the cart, that his speed wouldn't change. And we know that that's not true. He should slow down. If you think about it, it's kind of like what we did in class with the one cart at rest and the other cart moving. And the cart that was moving, remember, we put more masses on it. And when we had them collide and they stuck together, they moved slower afterwards. And so we couldn't use conservation of momentum here because the momentum of Bob before is not the same as the momentum of Bob after. However, if we choose the system to be Bob and the cart together, and I draw a free body diagram, I get the weight of Bob and the cart down, the total weight of the system down. I get the normal force up, which is the force of the road or whatever he's on, up on Bob and the cart. And there are no horizontal forces now because all those forces, no external forces, because all those forces are internal. And now momentum is conserved. So I can say that the initial momentum of Bob and the cart before is equal to the final momentum of Bob and the cart after. So let's do this. Let's use Bob and the cart as a system. So we have our initial momentum is equal to our final momentum. And my initial momentum, right, that would be mass of Bob times the initial velocity of Bob plus the mass of the cart times the initial velocity of the cart. That's my initial momentum. That's equal to my final momentum, which is the mass of Bob times the final velocity of Bob plus the mass of the cart times the final velocity of the cart. Now, if I look at this equation, I know that originally the cart's at rest, so that makes that quantity 0. I want to find the velocity of the cart after Bob jumps on. Well, that's the same as the velocity of Bob. So these two velocities are the same, and I can factor them out. So that leaves me with this as my equation. We'll pull out the masses because they are now stuck together as the system times the final velocity of Bob plus cart because they're together. Now I'm going to rearrange this to solve for the final velocity. V final of Bob and cart is equal to the mass of Bob times the initial velocity of Bob, right? That's the initial momentum of the system because Bob's the only one moving, divided by the total mass afterwards, which is the combined mass of Bob and the cart because they're both moving together. And now it's just a matter of plugging numbers in. The mass of Bob is 75 kilograms. His initial velocity is 4. And we're going to divide by the total mass of the system, so that's the mass of Bob, plus the mass of the cart. All right, 75 plus 25 is 100. So 75 times 4 divided by 100 gives us 3 meters per second, which is slower than 4. And that should make sense because momentum, if mass goes up, speed goes down. And when Bob jumps on the cart, now his total mass is up, which means his speed has to go down. And momentum's conserved because there are no external forces. All we're looking at is the interactions between Bob and the cart. Now, there are a bunch of different types of collisions. There's elastic collisions, there's inelastic, and there's totally or perfectly inelastic collisions. I'm not going to talk about elastic or inelastic collisions in this unit because they have to deal with the law of conservation of energy, which is something we're going to talk about in our next unit. But I do want to talk about perfectly inelastic collisions. A perfectly inelastic, I also call this a totally inelastic collision, is a collision in which the objects stick together. And that means that if they stuck together, right, they have to have the same final velocity. An example was Bob and the cart, right? They moved together afterwards. When we did the little lab activity, when those Velcro sides stuck together, right, that was a totally or perfectly inelastic collision. You're going to see some problems where we shoot bullets into blocks. There's another example. You'll see those actually more when we do energy. But that is another totally perfectly inelastic collision if the bullet stays in the block. Of course, if it shoots through the block, then that's not a perfectly inelastic collision. But so definition. Now, another type of collision is really the opposite of that. It's called an explosion. And in an explosion, we're starting off with an object at rest. And so that means it has zero initial momentum. And if there's an explosion and they move apart from each other, the law of conservation of momentum, because now these forces are all internal forces, they're forces within my system, right? Sometimes they're within the object, like my rocket here. Momentum will be conserved, which means the final momentum has to equal zero. Well, if the objects are moving, how does the final momentum equal zero? Remember, momentum's a vector. So if we take a look at our rocket example here, right, we have a rocket fuel system before, and say it's at rest on the ground, right, and it blasts off and the fuel shoots out. And so the rocket goes up and the fuel goes down. And remember, this would be a positive momentum and this would be a negative momentum. So they will add to zero. The initial momentum equals the final momentum in a collision. Now that's true in all dimensions. So if I have an exploding bowling ball, this looks like a bowling ball, doesn't it? Because it's got little finger holes. An exploding bowling ball, right, initially is at rest, which means that the total momentum initially is zero, which means the final momentum, when I add it up in all dimensions, has to also equal zero. So conservation of momentum is a great way to find out information about speeds of objects after collisions. Let's do one last example. I have a rifle. If you've ever shot a rifle before, you know that it has kickback. Right? And it has to, because this is an explosion. The bullet goes forward, so it has a momentum forward, which means there has to be momentum backward. They have to cancel each other out, so the total momentum is zero. So what I want you to do is pause this video and see if you can solve this problem. Well, if we use our law of conservation of momentum, right, our initial momentum has to equal our final momentum. Now, the initial momentum is zero, right? The bullet and the rifle are at rest before you shoot it. You want it to be at rest, right? Or you're going to miss your target. And that has to equal the final momentum, which is the mass of the bullet times the final velocity of the bullet plus the mass of the rifle times the final velocity of the rifle. So if we rearrange this, right, we're going to get mass of bullet times the velocity final of bullet. And so we're going to make that negative because we got to move that over to the other side, plus mass of rifle times final velocity of rifle. I want to solve for what is the final velocity of the rifle. What is that kickback? So if I do that, I get that the final velocity of the rifle is equal to a negative mass of bullet, final velocity of bullet, divided by the mass of the rifle. All right, that's just rearranging, doing some algebra. Now I'm just going to plug in numbers. So the final velocity of the rifle is equal to a negative bullet is 0.03 kilograms times the velocity of the bullet afterwards, the final velocity, which was 15 meters per second, divided by the mass of the rifle, which is 1.2 kilograms. If we solve for that, we get a negative 0.38 meters per second. Notice the negative because it's moving in the opposite direction, right? Momentum has to be conserved. So the momentums of each have to be equal. So how do you minimize that kickback? Well, if the momentums have to be equal, and momentum is mass times velocity, and the speed of kickback, right, the speed of the motion afterwards is really what's providing that kickback. If we increase the mass of the rifle, we'll decrease the speed because they have to multiply to the same number. Of course, that means the rifle's heavier, so maybe it's harder to hold, but at least it won't kick back as hard. All right, that's it. Fill out your WSQ, answer your questions, and I'll see you in class.